We have evaluated the loss of mode expectations for this daily peak load and number of occurrences, a chronological, or you can say number of loads and number of occurrences, peak load. Now we will see how the load duration curve. So what is a load duration curve? Load duration curve means load duration curve, suppose that was the load. So we write load and number of occurrences equal or exceeded. Okay. Number of load equal or exceeded. For example, to start with, suppose these are the loads 100, 90, 50, 70, 60, and so on up to 0 megawatt. So for how much time load exceeds 0 megawatt? It should be 100%. Okay. Similarly, it will go on reducing. 94, suppose 84, 75, 69, like that. Now you revert this table. So we take a reverse percentage. For example, what is the percentage of time the number of load is equal or exceeded for the lowest load? 100%. Then we plot like this. So daily peak load, which is this one. Okay. And what you get here, time the load exceeds the indicated value. This figure is from this book, reliability evaluation. Okay. So that means this is 100% of the time, 365 days. Suppose we are considering a year, 365 days means 100% of the time. Now this is the load which is there for all the days, minimum. So this is generally known as what load?
Balance. Base load.
Base load. Known as the base load, which remains constant throughout the year. Now this is exceeded 100% of the time. But there are some load, the maximum load, say I will say somewhere here. Okay. So this load is only available for 10% or more, or that means only 36 days. 36 days or more. Okay. This is 36 days or more. So if you take randomly, and this is our installed capacity, this is the load, this is the installed capacity. Generally the installed capacity should be much more than the peak load. Consider the outage okay. So this will result in only this much of load which can be made. Okay. But you see, if you take the loads in this side and the outage is okay, the load will not be made. Okay. The load will not be made. So this is the principle that we will apply for evaluating loss of load expectations using load duration curve. So all of you draw this curve. All of you draw this curve.
The region.
This is the result. Okay. Result means actual capacity available is this, but there are some more units which can take the installed capacity further if required. Those are known as operating reserves. Okay. We have also the reliability evaluation of operating reserves in module 3. Drawn and write what is okay and what is TK, because we are going to use this for solving the problem. Okay, write what is okay, what is TK. Which one?
QK.
Okay.
QK.
That is O. By mistake. take this little q is O. Okay, this is there. Okay, will you write? Okay, so I am going to the next slide. Write it down. So what is the formula for using LOLE using the load duration curve? In the first part we saw LOLE using normal peak load versus number of days it is occurring. In the second case we are using LDC, load duration curve. A particular capacity outage will contribute to the system LOLE by an amount equal to the product of the probability of existence of particular outage and the number of times units of the load. Okay, loss of load. So from the figure, LOLE for using LDC will be given by summation P equals to 1 by Pk Tk. Okay, write it down. This is exactly the same as the earlier one, but in this case we are using the loss of load probability from the load duration curve. So as I said, for the particular case, okay, anything which is within the 0 to Tk and if the capacity outage is more than OK, the loss of load will occur. So the probability Tk will be based from the curve. Okay, and Pk will be the value of that outage from the probability capacity outage table. Right? And the cumulative, and this is using cumulative probabilities. Okay, so this two you write. The reciprocal of LOLE is sometimes referred to as reliability index. The reciprocal of LOLE is sometimes referred to as reliability index. Right. Now we'll see how we use this formula for a particular problem. So this is the example using LDC, load duration curve. Now compute the loss of load expectation for a system containing 540 megawatt units. So indicatively write the statement of the problem. So 540 megawatt units. So that means 5 into 40, 200 megawatt is the capacity. Okay. And in this case FOR is 0.01. The system peak load what is represented by a load variation curve, peak load variation curve. The study period is 1 year and 100% in the axis means it is cumulative. This is the problem from this book, Willington Allen. Okay. Now your job is first draw this LDC. This one. So what you understand from here? 100% of the load. This is 100% of the load. This is 40% of the peak load. Okay. And 40% of the peak load is the base load, which is occurring for 365 days of the year. Okay, so draw this curve. Quickly draw this curve. Both of it.
More than 0.01
FOR draw FOR FOR is utilized for finding the generator reliability model, capacity outage table. Whereas this is for load model. These are two different things. We are just combining them to find the LOLE. Okay? FOR is not used. Now this whole problem boils down to how to find the TK. How to find the PK. Now for this particular problem, it is not given in the question. It might be in the problem set. So for this particular problem, what is the capacity? What is the capacity? The peak load given, this is actually given, the peak load that is equal to 160. Okay. The peak load is 100% means 160 megawatt. Okay, that is given. Now we have seen that 40% is the base load. So what is the 40% case? So if 100% is 160, so what is 40%? 160 into 0.4, which is
64.
Remember that 64 megawatt is available 100% of the time. Okay? So 64 into 1. 64 into 1. Then we have to find out 50%, 75% so as to obtain the corresponding time. Okay. Now suppose 50% of the time. Okay. 50% of the load. What is 50% of the load? 80 megawatt. Peak is 160 50%, 80 megawatt. Now we have to find out the corresponding time. This one. This time we have to find out. How you get that is 83.4%. So you can plot the curve and obtain that, but we can use the similarity of triangle between this and this whole triangle. Okay, that means what is the value of this? 40 to 100. 64 is this one. This one is 64. 40% is 64 megawatt. This is 160 minus 64.
Then 96. So 96.
90?
96.
96? Sure. So this is 96 divided by this is 100%. 100. That must be equal to this one
80.
sorry up to this
80.
that will be 80, right? 80.
Yes, sir.
80 by x. This t, suppose we will say that tk2. Okay. So what is tk2? Calculate. 80 by 96 into 100%. How much? Find out. 80 by 96 into 100%.
So 83.33.
83.4. 83.4%. Similarly, you can get for this value also. Using the similarity of triangles. Right? Using similarity of triangles, you can also get this value also. You can get. Then we have to use this formula. Probability into the time. So this is what I just show you. This is from the book. This is what I just show you. Okay, from the book. And the answer is given in this. So load direction. So this is from the book, and this is the information that I got from this diagram. Okay. So we go to the question number 2. Okay. So if you see here. So these are the values 160, 64, 120, 80, all these values from the curve, okay, and the corresponding time. Okay, slope of the curve that is given. Okay, total units are 40 into 5, 200 megawatt total capacity, and here up to this is same as you said FOR. FOR will be used here up to this to find out the capacity of the stable. So for that we need FOR. So this is the COT part. Now this is the load model. This is the load model using LDC. Okay. Now as we said, these probabilities we will multiply with what is LOLE? PK into PK. Okay. The other one using cumulative probability also you can do and into the other formula, but we are directly using this one into this one. Then you add up. So individually, percentage wise, day wise, or years per year. So this is days per year. This is the reliability of this system using LDC.
year per days की days last
It is days per year, but it is also, I told you, reliability index is equal to 1 by LOLE. Just before slide. So this is that reliability index. Okay. Now this completes your LOLE. The next part is actually that you read on your own. Only the theoretical part is there. So no, not this. This we will see in the next class. So we saw which lesson? This one.
lesson 6
Capacity expansion analysis. Okay. So just go through it. It's a theoretical part. Okay. So what is meant by capacity expansion analysis? It simply says that you go on adding capacity and compute the reliability index. Okay, or the LOLE. Now based on whatever the requirement, based on the reliability index or LOLE, we stop there. Expanding the capacity. There is no point in expanding the capacity beyond certain value, which will make the reliability index much better, but it is very costly. So that thing is known as capacity expansion analysis. Okay. So this completes your LOLE part. Okay, we'll stop here.